I'm Dario Santonoscito. I'm a PhD student from the University of Messina. Today I want to talk to you about the thermographic analysis during tensile test and the fatigue assessment of an S355 steel. It is common structural steels, and in this work we adopted a series of full field techniques like the digital image correlation and the infrared thermography. In particular, the displacement and the strain of the material were assessed through the DAC, while the temperature trend of the specimen surface was monitored during the tensile test with the IR camera, and also in the static and in traditional fatigue test. But the real aim of our work is that the fatigue properties are of fundamental importance in the mechanical design, but in the other end they are also extremely time consuming. So adopting an energetic approach like the static thermographic method, we can easily correlate the temperature trend to the fatigue properties of the material. A bit of theory, starting from the thermographic method. Since the first publication in 1987 in National Italian Congress to the milestone paper by La Rosa and Resitano of the 2000, during the high cycle fatigue regime, if we cyclically load a specimen with a load above the fatigue limit of the material, and we monitor the temperature of the specimen, what we can see is we can distinguish principally three phases. A first phase with an initial rapid increment of the temperature until a stabilization temperature, and it becomes the phase 2 with the plateau region. Then in the phase 3 there is a very high increase in the temperature of the material. On the other hand, for a load below the fatigue limit, we don't have any thermal increase in the specimen surface. If we calculate the integral of the temperature versus the number of cycles, we can assess an energetic parameter called phi. This energetic parameter is constant, so given a series of increasing stresses, we can assess that the stabilization temperature will increase also, but the parametric energy parameter is a constant of the materials. So we can plot the stabilization temperature for the different stress level at which we test the materials versus the stress level. And we can make a linear regression, and then the intersection between the linear regression and the stress axis give us useful information about the fatigue limit of the material. Another improvement, we can plot the SM curve of the material, because as we previously said, the phi is a constant of the material. So knowing the stabilization temperature, I can easily retrieve the number of cycles at which the specimen will be break at that stress level. Another improvement in the thermographic methodologies came in 2009, when Resitano analyzed the temperature trend during a static test. And we can distinguish three phases. A first phase where there is a linear decrement in the temperature, and where we can measure the thermoelastic coefficient. A second phase in which the temperature deviates from the linearity until at zero derivative flex. And the third phase where there is a rapid increase of the temperature of the specimen until the breakage of the specimen. And it is important to note that the change between the phase 1 and phase 2 can be related to a stress level that we can assume as a sigma of damage that introduces in the material a damage mechanism that anyhow we load the specimen, it will break. So it is the first microplasticity inducted in the material. Let's have a look at material methods. The steel that we analyze is a 355 steel with a nominal cross-sectional area of 15 per 10 millimeter. And the important things that I want to stress is that material comes from in-service component. It is from a crane of for harbor operation. And all the tests were performed with a servo-hydraulic load machine of the Eastron 8854 series. And during the test, an ear camera and a DAC system with a sample rate of 1 Hz were used. The specimen surface was covered with black paint in order to increase the thermal emissivity of the specimen in one side, and in the other side the specimen were coated with a black and white pattern in order to assess the displacement with the DAC. Two series of tests were performed. A series of static tests were performed on 3 specimens with a constant stress rate of 183 megapascal per minute, and a second series of fatigue tests were performed on 15 specimens with a stress range from 160 to 260 megapascal with a lower ratio of -1 and a test frequency of 20 Hz. The DAC technique allows us to assess the displacement and the strain on the specimen. In particular, we can see how the thermal area are strictly related to the zones of the specimen with where there is a strain concentration. And also the DAC allow us to assess the mechanical properties of the materials also in the plastic phase, and we can retrieve useful information like Young modulus, Poisson ratio, and the yield stress, and also the work hardening exponent of the Holloman equation. So if we analyze a static test and we plot the applied stress versus the experimental surface temperature relieved on the specimen versus time, we can distinguish a first phase where there is a linear decrement of the specimen surface temperature, and then a second phase where the temperatures slow down until a minimum region. If we make a linear regression of the two different zones and make the intersection between this linear regression, we can assess the fatigue limit of the materials and it can be easily read in the stress axis. For the test, we show that the fatigue limit determined by the static thermographic method changed between 116 and 180 megapascal. In a series of fatigue tests were conducted with a load ratio of -1 and a test frequency of 20 Hz. And the runout was imposed at 2 million cycles, and the fatigue limit is 176 megapascal. That is in line with a value present in literature. And it is important to note that the value predicted by the static thermographic method is between the range. So the value predicted by the static thermographic method agree with the traditional fatigue test. So in conclusion, the full fit techniques allow us the study of the mechanical characteristic of the S355 style. The DAC help us in the assessment of the strain field and the displacement field. And the higher techniques allow us the application of the static thermographic method in order to assess the fatigue limit of the component. And the prediction by means of the static thermographic method compared with the traditional procedure give us values that are in good agreement. As a summary, I report the value. And so the static thermographic method is a valid help in order to rapidly assess the fatigue properties of the materials. Thank you for your attention.
Thank you, Dario.